Hello everyone. Today we will be discussing about Lewis structures and resonance structures. We will be learning about what a Lewis structure is, and then we will look at the Octet rule, and then we will discuss drawing Lewis structures. And under this, we will first discuss the rules for drawing Lewis structures, and then the procedure that we follow while drawing Lewis structures. And then we'll also be looking at resonance structures. So first of all, what is a Lewis structure? A Lewis structure is a representation of bonding in which shared electron pairs are shown either as lines or as pairs of dots. So if you take the first example, the water molecule, the shared electron pair between oxygen and hydrogen is shown by lines like this. So this is a shared electron pair because both oxygen and hydrogen are forming a covalent bond by sharing their valence electrons. So this is represented by a line or by a pair of dot cross. So instead of this, you can even have a dot and a cross like this. And lone pairs are shown either as pair of dots or crosses. So here, as you can see, lone pairs are represented by dots. So the second molecule is N2, nitrogen. So here, as you can see, there are three shared electron pairs that form the bond. So we draw three lines to represent a triple bond. And these are the lone pair of electrons. In carbon dioxide, there are two bond pairs. So we draw two lines. And the final example, sodium chloride, which is an ionic compound. So in this case, sodium gives one electron to chlorine. So that's why that is this electron here, the X that is shown here. That is the electron that sodium gave to chlorine, and chlorine accepts that electron, and due to the electrostatic difference, a bond is formed. So next we'll be looking at the octet rule. So what the octet rule is that any atom other than hydrogen tends to form bonds until it is surrounded by 8 electrons and tends to acquire the electronic configuration of stable noble gas configuration of NS2-NP6 in the valence shell. So in the periodic table, noble gases have the configuration NS2-NP6. These are the 8 electrons that all the other atoms also tend to acquire. This rule is specially applicable for small atoms such as carbon, nitrogen, oxygen, and fluorine. The electrons, called an octet, make 4 pairs of opposite spin in the outermost s and p orbitals. But there are many exceptions to this rule, especially in odd electron molecules. So you might know that nitrogen forms molecules where the total number of valence electrons is an odd number. In these cases, nitrogen or in other atoms tend to break the octet rule. So if you see neon, you have a 2s2 2p6 configuration. Argon 3s2 3p6. So this is the configuration all the other atoms acquire. So now under drawing Lewis structures, we will first look at the requirements. All valence electrons of the atoms in a Lewis structure must appear in the structure. Remember, it's just the valence electrons that need to appear. All electrons are not shown, only the valence electrons are shown. Except for odd electron molecules, usually all the electrons of a Lewis structure are paired. So if there's an odd electron molecule, one electron will not be able to be paired. Other than that, everything else must be paired. Second period nonmetals, carbon, nitrogen, oxygen, and fluorine usually obey octet rule. So again, the exception are the odd electron molecules formed by nitrogen. Sometimes multiple covalent bonds are needed to construct the Lewis structure. So as you saw in the first examples, N2 and CO2 had triple bonds and double bonds respectively. So sometimes multiple covalent bonds are needed. Now we'll discuss the procedure for writing a Lewis structure. Step 1. Determine the total number of valence electrons in the structure. So for molecules, what you can do is you sum up the number of valence electrons for each atom. So carbon in its valence shell, in the electronic configuration, you know the electronic configuration is 2s2 2p2. So there are 4. For oxygen, you know the configuration is 2s2 2p4. So that 2 plus 4 is 6. And we have 2 oxygens, so 2. You multiply by 2 and you get 16 as the answer. For polyatomic negative ion, add the number of negative charges to total valence electrons. So the same way you get for carbon and for oxygen. So that is what is shown here. Then to represent this minus 2, you add 2 more electrons and you get 24 as the answer. For polyatomic positive ion, subtract the number of positive charges from the total number of valence electrons. So nitrogen, you know, has 5, hydrogen 4, hydrogen has 1, and there are 4 such hydrogens, so you multiply by 4, and to represent this plus, you subtract 1. So that is shown here, and you get the total as 8. Step 2. Identify the central atom. So there are certain ways you can identify the central atom. So usually the central atom is the atom with the lowest electronegativity. But there are some exceptions at times. Hydrogen and fluorine are never the central atom because hydrogen can only form one bond with another element. So hydrogen cannot be a central atom. Fluorine is the most electronegative atom in the periodic table. So it also can't be the central atom. Oxygen, which is the second most electronegative element, can be the central atom in certain cases. And those cases are O3, which is ozone, OF2. So OF2, since fluorine is more electronegative than oxygen, oxygen has to act as a central atom. And also in hydroxyl and peroxyl groups. So this is an hydroxyl group. Oxygen connected to hydrogens. The peroxyl linkage is this. 2 oxygens connected to each other. This is the peroxyl linkage. So these are the only cases where oxygen acts as the central atom. Carbon atoms almost are always central atoms. Step 3. Join the skeleton. Join the other atoms to central atom as necessary by single covalent bonds. So this is just like a human skeleton. You just connect all the atoms together by single bonds. Step 4. Calculate the number of remaining electrons. So after drawing the bonds, you know how many electrons you have already drawn and you know the total number of electrons. So using that, you can calculate the remaining electrons. Step 5. Distribute the remaining electrons over the skeleton and complete the octets of terminal atoms first. Then, to the possible extent, complete the octets of central atoms. The first you complete the octet for the terminal atoms and you finish adding all the remaining electrons. And then if it's possible, you can form bonds and complete the octet of the central atom. Step 6. If the central atom lacks an octet, make multiple covalent bonds by connecting lone pair electrons from terminal atoms into bond pairs. Assign the formal charges to the Lewis structure and check the stability. Formal charge rules will tell you which is the most acceptable Lewis structure for the given molecule. Step 8. Even after the application of formal charges, if you have a choice of Lewis structure for a given molecule, apply resonance to select the most acceptable Lewis structure. So we'll be looking at these 3 steps in detail in the next few slides. So first of all, formal charges. So for formal charges, it's the method that you use if there are more than one acceptable Lewis structure for a given molecule. And using this concept of formal charges, you can determine the most stable molecule, the most stable Lewis structure. The formal charge is the electrical difference between the valence electron in an isolated atom and the number of electrons assigned to the atom in the Lewis structure. So the formula is formal charge is equal to total number of valence electrons in the ground state minus the total number of valence electrons in the bonded atom. So by subtracting this, you can get the formal charge. When assigning charges to an atom in a Lewis formula, following assumptions are being used. The first assumption is bonding electrons are equally shared between two bonded atoms. So it means that the bonding electrons are exactly located in the center of a bond. That one atom does not draw the bonds to the electrons towards itself. You assume this. And electrons of each lone pair completely belong to one atom. So based on these assumptions, we can rewrite the previous formula. So we can divide the number of electrons in the bonded state into the number of lone pair electrons in the bonded atom. Now these electrons, according to this assumption B, completely belong to that particular atom, plus half the number of bonded electrons around the concerned atom. So since we assume that bonding electrons are equally shared between two bonded atoms, out of those two electrons that make up a bond, one of them belongs to this atom that we are currently taking the formal charge for. So that's why you put the half here. And then after you obtain the formal charge, you can apply the following rules to select the most suitable Lewis structure. The sum of formal charges of the atoms in a Lewis structure must equal to 0 for a neutral molecule and must be equal to the ionic charge of a polyatomic ion. So if it's neutral, remember always the formal charge sum must be 0. And if it's an ion with a charge, it should be equal to the charge. Remember, this is the sum of formal charges. So you need to add all the formal charges. Individually, each atom can have a formal charge that is not equal to the charge of the ion or the molecule. Usually, the most preferred structure is the one with no formal charges. Smaller formal charges, whether positive or negative, are usually preferred. So the small magnitudes are preferred over larger ones because it's more stable. Having the same non-zero formal charges on adjacent atoms is not preferred. So if you have the same non-zero, either two positive charges or two negative charges next to each other, you know that like charges tend to repel. So if you have, let's say, two positive or two negative atoms next to each other, then they tend to repel from each other and break the bond. So therefore, it's not stable. When two Lewis formula for a given molecule have the same magnitude of formal charges, then the one with the negative formal charge on the most electronegative atom. So the negative formal charge should be on the most electronegative atom, because the most electronegative atom tends to draw electrons towards itself, and having a negative formal charge on it is stable, and the positive formal charge on the least electronegative atom. So the least electronegative atom draws electrons to itself less than the other atoms. So having a positive charge on it is more stable. And therefore, that structure is the preferred Lewis structure. So now let's draw some Lewis structures. So first structure is formaldehyde CH2O. So we calculate the valence electrons. So carbon, if you look at this periodic table, the configuration is 2s2 2p2. So we have 4. Hydrogen, that's just one valence electrons. So we have 1. And since there are 2 hydrogens, you multiply it by 2. Oxygen, the configuration is 2s2 2p4. So there are 6 electrons. So you add them and you get 12. Now central atoms, so carbon is usually a central atom. Hydrogen can never be a central atom, and oxygen is electronegative, so it must be carbon. So now you draw the skeleton. So this is the skeleton. So carbon, and you draw single bonds between carbon and all the other atoms. The remaining electrons, so we have 12 electrons total, and the remaining is 12 minus 2 into 3. So this 3 is the total number of bonds that we have formed. So we have formed 3 bonds here, and 2. 2 is because each bond has 2 electrons. So we have 2 electrons being shared here. So we multiply 2 and 3, and so 12 minus 2 into 3, that's 6. Now we distribute the remaining electrons. So we have 6 electrons left to distribute. So hydrogen, we can't distribute any more electrons because there can only be 2. So all the 6 we distribute on the oxygen. Now here carbon does not complete an octet. It only has 6 electrons around it. So because of that, lone pair and oxygen should be converted to a bond pair. So I convert this lone pair to a bond pair. And that is our final structure. This is the structure of formaldehyde. Sulfate ion. So again, the same procedure, sulfur and oxygen 6. So you calculate the total number of valence electrons and then added electrons. So here, as you can see, sulfate has a -2 charge. You add 2 more electrons and you get 32 as a total sum. Central atom, it has to be sulfur, and the skeleton again sulfur connected to 4 oxygens. And remaining electrons, so we have 32 totally. We have drawn 4 bonds, so there are 8 electrons that have been drawn, so we have 24 left to draw. Let's distribute the electrons. So in the first example here, I have distributed all 24 among the oxygen atoms as lone pairs. So if I calculate the formal charge for oxygen here, as you can see, there are 6 lone pairs and there's 1 bond pair. Now in this 1 bond pair, there are 2 electrons, but only 1 is belonging to oxygen. So there's 6 plus 1. The total of 7 electrons around oxygen. But in the ground state, oxygen has just 6. So there is 1 excess electron. And to represent that excess electron, I put the formal charge of -1. It's the same case for all the oxygens. You have formal charges of -1 everywhere. Sulfur here, so there are 4 bonds and there are 8 electrons around sulfur. But since it's the bonded pair, only half of that number belongs to sulfur. So half of 8, that is 4, belong to sulfur. But sulfur in its ground state has 6. So it has 2 less electrons. So to represent that, I put a +2 formal charge. Now what we do is we distribute the electrons and form double bonds. So I send this here and I form this second example. Then again, I can still send even more and I get this structure. I can keep on forming double bonds. So here I have sent this and I form another double bond. I can still form another double bond. One thing to note here is that sulfur is in the third period. So because of that, sulfur has d orbitals. So sulfur can have more than 8 electrons in its valence shell. So sulfur can have a total of 18. So in any of these cases, so if you take the last example here there are just 8 bond pairs. So there are a total of 16 electrons. So we still haven't exceeded the total number of electrons that can be around sulfur. So this is just a point to note. Remember that second period elements cannot exceed 8 electrons in their valence shell. Third period electrons can go up to 18. Now among these 5 structures, which one is the most stable structure? So let's apply the rule of formal charges and see. So in the first one, you can see there are a lot of formal charges on every atom has a formal charge. So it can't be stable. And compared to this structure, here there is less formal charge distribution. So here, as you can see, this oxygen is neutral. So here only these 4 atoms have formal charges, and compared to this structure, the sulfur has just a +1 formal charge, whereas here it's a +2. So this is more stable compared to this structure. So the second structure is more stable. Now, if you look at the third structure, there are just 2 atoms that have formal charges. And those 2 atoms are the electronegative atoms that are oxygen. So this third structure is even more stable compared to the second structure. If you look at the fourth structure, you will see that there's a negative formal charge on sulfur, and sulfur is the less electronegative atom, so having a negative formal charge is not good for sulfur. And also these adjacent atoms have negative formal charges, so they tend to repel. So this also is unstable. And the final structure, sulfur has a large negative formal charge. The central atom having a large negative formal charge is not preferred. So the last structure is also unstable. So this structure, the third structure, has to be the most stable structure. And we'll be continuing this further under resonance structures. Example 3, carbon monoxide. So again, carbon 4, oxygen 6. And since there are just 2 atoms, you can't define a central atom. So skeleton, again carbon and oxygen, and remaining electrons 10 minus 2, 8. So now let's distribute the electrons. So among those 8, I distribute 6 to oxygen and 2 to carbon. Now let's complete the octet of carbon. So here oxygen has already completed the octet, but let's complete the octet for carbon. And now octet, the carbon atom has also completed the octet. Now another structure that we can come up with is this, where instead of giving away 2 lone pairs to the bond, one oxygen gives us one lone pair to form a bond. Now here carbon hasn't completed the octet, but oxygen has. Let's compare these two structures. Here there's a 0 formal charge distribution, but here there's a +1 and -1 formal charge distribution. So again, no formal charges. And here the positive formal charge is on the electronegative oxygen atom. So as you can see, there's a positive formal charge here on oxygen, which is more electronegative than carbon. But here in the first structure, only oxygen has completed the octet. But in the second structure, both the atoms have completed the octet. And in reality, the structure of carbon monoxide is this. So therefore, we can come to the conclusion that for small atoms such as carbon, nitrogen, oxygen, and fluorine, the octet rule is the superior rule. Remember that the octet rule is the rule that must be satisfied by small molecules. The exceptions are odd electron molecules. Alright, our next topic is resonance structures. For certain molecules, one structure is not enough to explain the correct bonding within the molecule. Therefore, 2 or more structures are needed to explain the bonding. And the multiple structures that are drawn to explain the structure of such a molecule are called resonance structures. However, remember that the true structure of a molecule is not equal to any of the resonance structures drawn, but is a hybrid of all the resonance structures. Only the resonance hybrid has physical reality. As an analogy, when the Europeans first saw the rhinoceros, they described it as a cross between a griffin and a unicorn. Now, one thing to know is that griffins and unicorns don't have physical reality, but the rhinoceros has a physical reality. So this is similar to what a resonance structure is. The individual molecules that are drawn to make up the resonance hybrid have no physical reality, but the final resonance hybrid has a physical reality. So again, resonance also has a few rules. The position of atoms are fixed in all structures. So as an example, if you take a look at these two structures, they look similar, but these two are not resonance structures. The reason is because the position of atoms has changed here. So here, as you can see, this carbon has two CH3 groups connected to it. But here there are three CH3 groups connected to that carbon. And here there's no CH3 group connected to this carbon, but here that carbon has acquired this CH3 group. So because of that, these two are not resonance structures of each other. Only the pi bonds or lone pairs may vary among contributing structures. So again, as in the first example, the sigma bond position has varied, but in resonance structures, only pi bonds and lone pairs can vary. All contributing structures must have acceptable Lewis structures. So carbon, nitrogen, oxygen, and fluorine must complete the octet, and they must follow all these rules. All resonance structures must have the same net charge, and this net charge is equal to the formal charge, and the formal charge should be equal to 0 in a neutral molecule, and it should be equal to the charge in a polyatomic ion. All rules that are used when drawing Lewis structures are to be used when drawing resonance structures. Most stable resonance structure can be determined the same way most stable Lewis structure was determined, that is using formal charges. The resonance hybrid has lesser energy than any of the contributing resonance structures, and the energy difference between the resonance hybrid and the most stable resonance structures referred to as resonance energy. So there is a certain term known as resonance energy, and this energy is the difference between the energy of the most stable resonance structure and the hybrid. Hybridization of a given atom is same in all structures. So you know about hybridization. There are different types of hybridizations, and hybridization should be same across all resonance structures. So sulfate, we are coming back to the sulfate. So we concluded this as the most stable Lewis structure. Now you can draw resonance structures like this. You have oxygen, you have the double bond here. Now remember, this pi bond here can vary. The pi bonds can vary, but the sigma bonds must remain the same. So now from there, I move the double bond here, and then I move it here, move them here, move them here, and move them here. So I vary the position of that double bond, and by varying the position, I get 6 resonance structures like this. Now let's draw the resonance hybrid. So when drawing the resonance hybrid, remember these sigma bonds should be shown. So these sigma bonds are shown by this line, these lines here. They should be shown by lines, and these broken lines show the bonds are not permanently present at that given location. So if you take a look at this bond here, it appears in the first structure. It doesn't appear here. Again, it appears here. It appears here. It's not here. It's not here. So it is available in certain structures and it's not available in certain other structures. And because of that, you draw a dotted line. And it's the same case for all the other 4 sigma bonds as well. So we draw 4 dotted lines like this. And then we have the charge, the formal charge that we have put for the oxygen atom. So the formal charge we have put is minus half. So how do you calculate the formal charges? You take a given oxygen atom. So we take this oxygen on top, let's say. And for all these drawn structures, you add the total charge. So here we have 0. So here we have minus 1. So we add minus 1. Again 0, 0, minus 1, minus 1. So we have 3 minus 1s. So by adding them, you get minus 3. Then we divide minus 3 by the total number of resonance structures drawn. And here we have drawn 6 resonance structures. So we divide minus 3 by 6. which is equal to minus half. That's how you get minus half. And similarly, by calculating it for all the other oxygen atoms, you can get minus half. N2O5. So this is the skeleton of N2O5. Now we are going to draw resonance structures for this. Again, we use the same procedure while drawing Lewis structures. We distribute all of the electrons and we complete the octet. So here, as you can see in the previous example structure, nitrogen lacks an octet. So we form bonds with oxygen and we have obtained nitrogen which has an octet. So this is one structure. Next, we can vary the position of this sigma bond, this pi bond, and by doing so we can get 3 more structures. So now we have 4 structures in total. After that, we can change the position of the pi bond that was here. We can change it here. So from here we are moving the pi bond here, and similarly now I move this pi bond here. So we have 2 more like that. Now I can do the same thing to the other side as well. So I move the pi bond here and I vary this here now. So we have 8, and the final 9th structure, which is really unstable, is by moving this pi bond here. So this final structure is really unstable because every atom has a formal charge. Oxygen has a +2 formal charge, and oxygen is the most electronegative atom. And nitrogens, which are adjacent to the oxygen, have positive formal charges. So here this is being repelled continuously. So this is a very unstable Lewis structure. But since they are asked for all the possible Lewis structures, you can draw 9. The third molecule is N2O. So again, we use the same procedure and we draw our Lewis structure. So we calculate the total number of electrons and we draw a skeleton. Here nitrogen should be the central atom because it's the least electronegative one. And then we distribute electrons among the terminal atoms. Next, we complete the octet by forming triple bonds like this. And now we just vary the position of this sigma bond. So here we have 3 and 1. We move 1 here and we get two double bonds. Then we move 1 more here and we get a triple bond and a single bond. So like this, we have 3 structures. Now let's compare the stability of these 3 molecules. So the first one, as you can see, since the formal charge is on oxygen and nitrogen and there's a +1 -1 formal charge, also the most electronegative atom, which is oxygen, has a -1 formal charge, and nitrogen, which is less electronegative compared to oxygen, has a positive formal charge. It can be considered the most stable structure. The second structure, compared to the first structure, nitrogen, which is less electronegative compared to oxygen, has acquired this minus positive charge. So this is comparatively less stable. And the third structure, as you can see, oxygen has a positive formal charge. Again, nitrogen has a positive formal charge. So adjacent formal charges. So this bond is being repelled. And this nitrogen has a -2 formal charge, so which is a large negative formal charge. So this is the least stable resonance structure. Now let's draw the resonance hybrid. So while drawing the resonance hybrid, since the third structure we drew was the least stable, was very unstable, it doesn't contribute much to the resonance hybrid. So while drawing the resonance hybrid, you can neglect that structure. So let's draw the resonance hybrid. So here you draw this sigma bond, which is permanent, and this pi bond is not permanent. So you draw a dotted line. Here, one sigma and one pi bond are found in both the structures. So you draw a double bond, and then this bond here is not found in both the structures. So we draw a dotted line there, and then we put the charges. So here you have -1 and 0, so minus half. Again, plus is found in both, so we just put plus. Here we have 0 and -1, so -1 divided by 2 is minus half. So this is the resonance hybrid for N2O. Now a brief summary. The Lewis structure is a representation of bonding in molecules. All valence electrons must be shown in a Lewis structure. Formal charges help you decide the most stable Lewis structure. Resonance structures can be drawn when more than one Lewis structure represents the actual structure of the molecule. The resonance hybrid represents the true structure of the molecule. So thank you for watching. I hope you all understood it, and I hope that this was useful.